Hi everyone. A couple of labs this semester are centered around using breadboards to physically build some digital logic circuits. This video will walk you through some of the basics of using a breadboard. Now, I'm going to assume that at some point in the past you've had a lesson or two on basic electricity where you took a battery and a light bulb, then connected them with wires to form a complete circuit. For the most part, these labs will be similar. However, our circuits will include some additional components like resistors, switches, and logic gates. One challenge when building circuits is holding the components together. That's where the breadboard comes in. At a high level, a breadboard is just a grid of holes organized into connected groups. If two wires are plugged into holes in the same group, then the wires are connected. Take note of where the groups are. First, each horizontal row at the top and bottom forms a group. You will wire your power supply to these groups. Second, each vertical column of 5 holes forms a group. These groups are your main workspace. Notice that the top and the bottom of the board are not connected. If you want to connect two wires, they either need to both be above the break in the middle or below it. Pause the video for a minute and make sure you understand where these groups are. Now, let's see how we use these groupings. It's especially useful to keep in mind the vertical 5-hole columns. So if I place the ends of these two wires in the same column, then they're effectively connected. There's a metal plate below the holes, so any electric signal flows from one wire through the metal plate below and into the other. However, if I put the wire ends in different columns, then they're not connected, because those metal plates are vertical, not horizontal. Also, remember that the two halves of the board are separate, so if I move the wires like this, they're not connected. They're in the same column, but one's on the top half of the board and one's on the bottom half of the board. Most of your kits have a power source that looks like this, a plug connected to two wires. Although it's hard to read, this plug provides 500 milliamps of current at 5 volts. For purposes of these labs, you can think of this as a 5-volt battery. And then here on the underside of this adapter, we can see which wire is the positive and which wire is the negative. I find it convenient to connect the positive terminal to the row at the top of the breadboard, the one marked positive, just so I don't get confused, and the negative terminal to the row at the bottom marked negative. Remember, these horizontal rows each form a group, so when we need to hook something to positive voltage or ground, we can use any hole in the corresponding rows. Actually, some breadboards are also disconnected left to right, so if it doesn't work, all you have to do is use a wire to bridge that gap like that. But that's not something you have to worry about unless you actually have a problem. Now, instead of a light bulb, we're going to use an LED. LED stands for light emitting diode. A diode is a device that only allows current to flow in one direction. That means, unlike a conventional incandescent light bulb, it matters which end is positive and which end is negative. For the LEDs in your kits, the longer wire needs to be connected to positive. Now in this picture, it's pretty clear which wire is the longer wire. And if you happen to have new LEDs in your kit, it is pretty easy to see which wire is the longer wire. In both cases here, the longer wire is on the left. Unfortunately, as these wires get used and manipulated, it's not always as easy to see which wire is longer. Like for this LED, the longer wire is also on the left, but that's not nearly as immediately obvious. Fortunately, there's no harm in guessing. If it doesn't work, just turn it around. We'll see that in a minute. Okay, I'm going to put this LED on the board. It's also a well-used LED, so you probably can't really see which wire is the longer wire. I'm pretty sure it's this one right here, so I'm going to put it on the board with the longer wire to the left. It's not necessarily important that the longer wire is to the left. That just helps me remember which end is which. Now I'm going to take a wire and put one end of it in the same column as that longer wire of the LED, and the other one in any hole in that horizontal row that represents the positive power supply. Now, if this was a regular incandescent light bulb, My next step would just be to simply connect the other end of the LED to the negative terminal of the power supply. However, LEDs are special. They're incredibly efficient. That's why we're putting them in light bulbs in our houses now. And they use very, very little energy. And so if I were to make that connection directly, it would allow too much current to flow through that circuit and would probably blow the LED. It could even damage the breadboard, but typically it just results in the LED blowing. What we need to do is we need to add some resistance to the circuit so that less current will flow, an amount of current more appropriate to the LEDs. And to do that, we use a component called a resistor. Here's an example resistor, and there are several kinds of resistors in your kits. For resisting LEDs, the important thing to notice here is the brown band in the middle. Resistors with a brown band in the middle have a resistance of between 100 and 1000 ohms, and that's the right amount of resistance for these LEDs. It limits current enough so the LED doesn't blow, but it doesn't limit it so much that the LED doesn't shine brightly. So we want to put this in the circuit. So to continue the circuit, we'll put one end in the same column as the shorter end of that LED, and we'll put the other end in a different column. It doesn't really matter which one. And now that we have some resistance in the circuit, we can complete it by putting a wire from the other end of the resistor into that negative row for our power supply. So here we have a complete circuit. So now if I reach down and plug the power supply in, the LED should come on. And the LED didn't come on. So now we have to figure out what the problem is. If you look right here, you can see that the wire and the LED are in different columns. That means there's a break in the circuit. So we need to fix that by making sure both ends are in the same column. And now the light comes on as expected. Now let me quickly remind you that LED is a diode. It only works in one direction. So if I were to have accidentally put that LED in backwards, nothing bad happens. The light simply doesn't come on. And so if this happens to you, if you have a complete circuit and you've checked to see that everything is in the right column and the LED still isn't on, just simply take it out and turn it around. Okay, let me pause and say a few more words about resistors. A resistor's strength, as I mentioned, is measured in something called ohms. The more ohms, the more it resists the flow of current. Another way to say that is a circuit with a higher resistance will have fewer amps flowing through it. All resistors have a series of colored bands on them to tell you how many ohms it provides. I've provided a link in the video description as well as on the lab write-up to a website that shows you how to calculate the precise number of ohms a resistor has based on the colors of the bands. As I mentioned, the LEDs in our kits are designed to work with resistors of several hundred ohms, and so those resistors will have that brown stripe in the middle. That brown stripe is a multiplier of 2, indicating that the resistor has hundreds of ohms. Some of your kits also have smaller resistors. This is a 330 ohm resistor, and it also has that same brown band in the middle. Now in a few minutes, we will also be adding switches to our circuits, and switches use resistors with a higher number of ohms. For example, this resistor has about 4,700 ohms, and it's this red band here is what tells you that it's a few thousand ohms. Or you might also have a resistor with an orange band in the middle, and this resistor is 10,000 ohms. So that middle stripe is the order of magnitude. So notice it changed colors as we went from hundreds to thousands to tens of thousands. And then let me remind you once again, every LED needs to be connected to its own resistor. If you have 5 LEDs on your board, there had better be 5 resistors with that brown band in the middle. If you're missing a resistor, you're potentially causing damage to something on the board. Okay, now let's get into some of the fun stuff. Let's add some logic gates. The logic gates in your kits come in chips that look like this. And typically each chip contains several gates. For example, this chip has 14 pins and contains 4 AND gates. Notice that this chip has both a circle in it and a notch in it. Now this circle has paint in it. We put that there to make it easier to tell which chip is which. In general, these chips are completely black. Notice that I'm holding this chip with the notch to the left. That's a standard that we'll follow throughout the course so the chip gets oriented the right way. So like I said, this chip has 14 pins, and this diagram shows how those pins are used. And again, just to emphasize, I've made this drawing with the notch to the left. The pins are numbered counterclockwise with pin 1 in the lower left and pin 14 in the upper left. Pins 7 and 14 are special. They supply power to the chip. They must be connected to the positive and negative terminals for reasons that are analogous to why you plug your computer into the wall. For this chip to execute its logic function, it needs power. And so these pins are where that power comes from. And if you're curious, VCC stands for Voltage Common Collector. I don't really understand the importance of that. I'm not an electrical engineer, but if you do see VCC on some diagrams, it just means the positive terminal of the power supply. And then also take a quick look here. You'll notice the other pins are either the inputs or the outputs to the logic gate. Okay, so let's go back and add this chip to the breadboard. So I'll move this wire out of the way for a minute. And notice these chips will always go across the middle, across that break in the middle with the notch to the left. You'll get tired of hearing me say that, but the notch has to go to the left. Things go downhill real fast if it's not. The next thing you need to do is hook this chip up to power, which, like I said, is analogous to plugging a computer into the wall. So I'm going to take this short wire here. I'm going to use short wires to help keep the breadboard from getting too messy. And I'm going to connect one end above pin 14, which is in that upper left-hand corner of the chip, and the other end into the horizontal row, which is the positive part of the power supply. Then I'm going to take another short wire, connect one end below pin 7, there in the lower right, and the other end to the negative side of the power supply. Now I want to wire up a logic gate. So I'm going to pick one of these 4 logic gates at random. I'm going to go with the one in the upper left. No special reason for that. And you can see that the output pin for that logic gate is pin 11. So 14, 13, 12, 11. I'll put a wire in the column for pin 11. And the other end, I'll connect that to the column with my LED in it. Notice they got off by a row there. And then the inputs to this logic gate are pins 12 and 13. Now I'm going to start out by hooking both of these pins to a logic 1. I want a logic 1 or a logic true as input to this AND gate. So I'll hook up pin 13 to positive and pin 12 to positive. Now, if this is all hooked up right, when I reach over and plug it in, the LED should go on, right? Because if the inputs to an AND gate are both logic true, then the output should be a logical true as well, which is shown here with the LED being on. If I instead take one of these inputs and tie it to a logic false, now I have a true and a false going into my AND gate, so the output should be a logic false, which is shown by the LED remaining off. Now you're going to find that physically moving these wires between true and false can get annoying and difficult. Typically what you want to do when you want to change signals in a circuit is you use a switch. So here we have what's called a dip switch, and this is just kind of like the switch on the wall. When the switch is on, it physically connects the two poles of the switch, the top and the bottom, and when it's off, it physically disconnects them. We're not going to use them right away, but later in the semester we'll also use what are called momentary switches. And these switches are always off. There's always a disconnect between the left and the right side unless you're physically holding down the button. Like I said, we'll come back to those in a couple of weeks, but for now let's talk about the dip switch. So what I want to do is I want to take one of my inputs and I want to run it through a switch so that I can see how this logic gate works without having to physically move the wires around. So let me first show you the wrong way to do this. And remember, what I'm doing right now is the wrong way to do it. You might be tempted to hook the switch up the way you would hook up a switch in your house, which is simply to put the switch in the middle of the path. So I'll start out by connecting positive to the top side of the switch, and then I'll go from the bottom side of the switch to that input pin. So now for the second input, the signal goes through the switch. And so far, so good. This input is hardwired to a logical true. This one is switched on, which also represents a logical true, and the LED is on, which is what we expect. But when I turn the switch off, nothing happens. So let me explain why this doesn't work. And this is important because overlooking this next step eats up a lot of time during these labs. So you want to make sure you're not making this mistake in the lab. So let me take the switch out for a minute. And let me just take this wire and plug it in. And again, we have two hardwire true inputs, and that's what we expect. And then when we take this wire and we hardwire a true and a false, the LED goes out like we expect. But watch this. Watch what happens when I pull the wire off the negative bus. The light comes back on. Notice the end of this wire is floating in the air, so we call it a floating input. Why does this floating input get interpreted as a logic 1? It's because logic 1 and logic 0 is determined by voltage, not current. Obviously, there's no current floating into pin 12 here because it's not hooked up to anything. But what's the voltage? Now, I don't want to make this too long, but briefly, voltage is a measure of electrical pressure, how badly charge wants to get from one point in a circuit to another. So our power supply is a 5-volt power supply. And what that measures is how much work the charge will do to move between the positive and negative terminals of that power supply. So in these circuits, a logical 1 is when there's a lot of pressure, like nearly 5 volts of pressure, for charge to move from that pin to the negative terminal of the power supply. Whereas a logic 0 is when there isn't much pressure for charge to move between an input pin and the negative terminal of the power supply. So what's the voltage right here? How badly does charge want to move between this floating wire here and the negative terminal of the power supply? And the answer is we simply don't know. It depends on a lot of things that we don't control, like the static electricity in the air, or maybe you shuffled your feet on the carpet before coming to the breadboard, or maybe you combed your hair right instead of left. Anytime you have an input to a circuit that isn't specifically connected to either the positive or negative terminal of your power supply, you have an unknown voltage, which means you don't know whether the chip is going to read that as a logic 1 or a logic 0. So the bottom line is, when you're doing these labs, every input pin needs to have a clear path to the positive or negative terminal of the power supply. Anytime you don't have that, you have a problem and you will likely have an error. Now, floating inputs can be subtle. So here, this is obviously a floating input because I'm holding the thing that's floating. But what if I just forgot the wire altogether? That's also a floating input because from pin 12 here, there is no path to either the positive or negative terminal of the power supply. this wire, this pin on the chip is effectively floating in the air. Now notice as I'm touching this and pointing it that light's flickering. A flickering LED like that is a sign of a floating input. As I move this wire through the air and its static electricity, and then I touch the pin, then that unknown voltage gets registered. Or especially if I'm holding the other end of the wire with my fingers, then you get some signal coming from the static electricity in your body, or you're, like I said, rubbing your feet on the carpet and whatnot. All right, so now let's think about another hidden floating input that's really common as you do these labs. So I'm going to put this wire back into the switch. The switch is turned on, so we're back to the normal expected state where that logic gate has two logic 1 inputs, the hardwired one and the one through the switch. Now what happens when I turn this switch off? When I turn the switch off, you may have seen the LED dim just a little bit. I am physically breaking the connection between the white wire on the top of the switch and the green wire on the bottom of the switch. This is exactly how your wall switch works. It physically breaks the connection between the input and the output, and then current doesn't flow. However, in this case, because the chips run on voltage, I've now created a floating input. The left end, the switch end of this green wire, is now floating. There's no connection to the positive or negative terminal of the battery. So it doesn't behave as we'd expect. What we need is to make sure that that wire does have a connection to the negative terminal. If I put that in there, then the light goes out as we'd expect, because now there's a clear path from pin 12 to the negative terminal of the power supply. Now this doesn't quite solve the problem, because if I were to turn this switch on, I would now have a short circuit. I would have a path directly from the positive terminal of the power supply through the switch, through this orange wire to the negative terminal, and that would cause a lot of current to flow. The breadboard would heat up, bad things would happen. So here's what we do. So if you've zoned out a little bit, here's where you can wake up and pay attention. This is the key thing you need to know when using switches in the lab. What you do is you first hook the switch up the way you think a switch would be hooked up, right? You just put the switch between the connection from the positive to the pin. But then you go and grab a kilo ohm resistor. This is a 4.7 kilo ohm resistor, again with that red band in the middle. And you put that resistor on the bottom side of the switch and connect it to the negative terminal of the battery. So now there is a clear path from pin 12 through the green wire, through the resistor, to the negative terminal of the power supply. So there is an unambiguous logical 0 going into that gate, which is what we want. Now when we turn the switch on, there are now two potential paths. The one we just described through the resistor to the negative terminal of the battery, and the one through the switch through the whitish grayish wire here to the positive terminal. But now, I'm sure you've heard the phrase, electricity follows the path of least resistance. Well, that's exactly what's happening here. We have two paths, one with effectively no resistance on it, that's the one from the positive terminal, and the one with 4,700 ohms of resistance on it. And so the one with no resistance is the one that counts, and so it registers as a logical 1. Unless you turn the switch off, then the only path is the one through the resistor, so that's the one that counts. It counts as a logical 0. Oh, there's one last thing you need to know before you get out and start working on your own, and that's how to take the chips off the breadboard. When it comes time to removing the chips, don't just grab them with your fingers. Use these yellow chip pullers. So what you do when you want to remove a chip is you take the chip puller, you hook it under each edge of the chip, and you pull straight up. That may seem like a small thing, but the problem is if you just use your fingers, you inevitably pull your thumb up or your index finger up faster. So it's very hard to use your fingers to pull the chip straight up. And so if you try to do it with your fingers and you tip the chip as you pick it up, then you end up flexing these pins on one end or the other, and they eventually break. So to prolong the life of our equipment, please be sure to use the chip puller. So now you know enough to get started on your own with your own breadboard kits in the first couple of labs, and I hope you have fun with it.